Hi class, so the next big thing we'll talk about with interactivity is this problem called hit testing. And it's basically the following situation. You have a viewport or a screen that you've rendered. And inside here we have a bunch of objects, right? Maybe we have a rectangle, maybe we have a triangle, maybe we have a circle, you have some kind of convex polygon, you might even have a complex concave polygon. Okay, you have all these objects in a space. And now I come along with my mouse pointer and I click. Okay, so I click, and the question is, did I hit any of the objects? Visually, of course, we can pick this out and we can see it. But we have to think about how to solve this in our computer graphics system. This is often also called picking, which is the problem of how to tell which object a mouse hit. You can imagine this is really important in a lot of cases. So it's not just this situation here. A 3D modeling software, I click somewhere and I move. Which object am I moving or rotating? A video game, I click to shoot or I click to select. Which object do I hit? So this is all part and parcel of this bigger problem of hit testing. Now the first problem we come across is that the mouse coordinates, which we get from our windowing system or our operating system, they're in viewport space. Right? So, for example, you could imagine that the top left corner is 0, 0, and the bottom right corner might be 640 by 640, right? So you're in viewport coordinates, basically mapping to the raster. Whereas the objects that we are trying to check against, they're not usually in viewport coordinates, they're in some other coordinate systems. Okay, so that's the first problem. And so in order to compare our mouse position or our selection position with the object locations, we need to make sure we're in the same coordinate system. We need to put both the objects we're comparing against and the mouse into the same. Maybe I'll highlight this. The mouse and the object into the same coordinate system to do our hit check. So you could imagine, for example, that while the mouse is in this viewport coordinates of 0 to 640 by 480, this rectangle, it might be in its own local coordinate system, where NDC may be. So this might be minus 0.8 comma 0.8, with the bottom right corner, say, being x of minus 0.5 and 0.5 up. So you can't compare that, right? They're different coordinate systems. It doesn't make any sense. There's a couple of approaches to this. We can do it during rasterization, because during rasterization, we're actually bringing all of the objects into viewport space. If we do it there, we just need to make sure, and we'll learn some techniques for that a little later, we just need to make sure that we keep track. You know, if we just throw a bunch of vertices at our engine and it crunches them and draws them in triangles, which object does that triangle belong to? We need to make sure we have a way of keeping track of that, okay? Another way to do it is we can bring the mouse to normalize device coordinates. So you can, for example, you can take the inverse of the viewport matrix to do this, because remember, the viewport matrix is set up to bring NDC to viewport. You can invert that, or you can just calculate using ratios. You know, this is not hard. So I have mouse X over width tells me the percentage across, and then I times that by 2. So 2 times that, now I range from 0 to 2, and then I minus 1, something like that. And that'll map me to -1, 1, and you just be careful with the y being in which direction and whatnot. Okay. Same for y. But watch y inversion, right? Because in processing, y goes down, NDC, y goes up, that kind of thing. So just be careful. That's all. So we can do it during rasterization. We can bring the mouse into NDC and do it there because this is like a meeting point, a standardized space. Or you could just bring the mouse all the way to object space. So you could imagine you have some model, I make a robot or something. I'm clearly not an artist. It's a robot on wheels, and it probably should be smiling. So we have a robot, and I want to click on, when I click on it in my canvas, I might want to know, was it an arm, was it a head, where in the robot, was it left or right? But after all the transformations it goes through, it can become really tricky. So if I do that, this is useful for detecting where in the object was clicked, because I work in the object space. Detecting, that's not a word. Let's try that again. Detecting where the object was clicked. Right? So that's really cool. And it's actually not difficult to do. You just invert the whole chain. So viewport, and then I have my projection, and I have my view, and I have my model. If I invert all of this, then it goes viewport to model space. So you can invert everything. Now, remember in the 3D section we learned about keeping that Z so it's invertible? This is an example of where that's really useful. If that Z coordinate goes to NDC and you keep that value, then you can on-project that with your matrix, okay? Yeah, you can do that. All right. The other thing I'll mention is this might take some trickery here. Depending what you're doing for your projection, it might be easily invertible. It might not be so straightforward. You'll need to understand your system to make that decision. But that's beyond the scope of this course. We're not going to go into that. Okay. Yeah, I'll just highlight. You might want to know whether a person hit here or hit a wheel. That could be very useful information. And if you're doing it in say raster space and the thing is turned and it gets really complicated to solve that, instead it can be easier if you're looking at it in your expected space. Okay, so that's an introduction to hit testing. So that's our problem here. We want to know where's under the mouse or under a cursor or under a point in our complex scene, and basically to do that we need to first make sure we're in the same coordinate space with our selection and our objects, and then we'll think about how to detect whether they're overlapping. Okay, so I'll come back and then we're going to learn a few methods, the basic methods for actually doing that kind of detection.